I'm Dr. Udar. So, on our this syllabus of engineering mathematics from the last unit, one topic is left, that is the Stokes theorem. So, let us cover it today so that our syllabus is complete. So, let S be a piecewise smooth open surface. So, in our earlier one, that is Gauss divergence theorem, that was the closed one. Here it is the open one. So, the surface is open and piecewise smooth means it is continuously differentiable one. That means, or in other words, in simple words, I can say that there is no sharp turn or edge there. So, that is the meaning of it, piecewise smooth, and it is open. Now, it is bounded by a piecewise smooth simple closed curve. So, it is bounded by it. So, I will explain these things below. So, these are the things given to us, and let f, that is a vector field, be continuous vector function. Basically, rather than continuous, it is a vector function which is continuous first partial derivative. That means the partial derivatives are also continuous. Then what does Stokes theorem says? That it relates the line integral over that boundary C to the curl of f and surface integral of it. Now, here surface integral here is represented by this. In certain books, it is written by this as well, and certain number of times it is written by n cap dA as well. Here I have written ds, n cap ds. ds is a small portion of the surface. So, here it is referred to as dA also at many places. That means small area portion, and certain places it is written like this also, that ds, n cap is merged there. So, these are the notations for it. So, line integral is related to the surface integral. This is the Stokes theorem. So, now let us understand it geometrically. C is traversed in the positive direction. It is taken by the right hand thumb rule, that where the n cap is. So, let us take say for example this one, this figure. Okay. So, here we are having a hemisphere, and hemisphere I am talking about this. So, here it is hemisphere and open from below. Below means this portion, lower portion. So, that means this is the lower portion and this is hemisphere above. So, this is the hemisphere. Lower portion is open-ended from below. Now, we are having this closed curve. This C is the closed curve, that from where it is open. So, now if I find line integral over this C of f dot dr, then it is nothing else but equal to the surface integral. That means integral over this surface of what? Surface integral of curl of f, and that is the surface integral. So, this is the meaning of it. Now, piecewise smooth means, here basically leave aside for the time being the open one. I take for the time being to explain the smoothness. If I take the sphere, basically that is the closed one. So, that is the, it is not only the piecewise, it is whole of the smooth, not in the pieces. I can take it in pieces as well, but it is smooth from each and every part, whatever part I can take. But suppose if I take a cube or cuboid, then that is the piecewise smooth, because if I take one portion, one face, then that is smooth. If I take another one, that is also smooth. So, there are 6 faces, all the 6 faces are smooth. So, that means it is piecewise smooth, if I am taking the 6 pieces. But as far as the sphere is concerned, so it is whole of the smooth one. So, this is the meaning of smoothness. Now similarly, if I take the cone here, so this is the, I am talking about this figure. So here this C part, lower part, that is open. So if I take the line integral over it, so it will relate by the Stokes theorem to the surface integral. Similarly, I can take the middle one now. So middle one, it is a open surface. So what is our C? C here is this boundary. This boundary is C. So if I obtain line integral over this, so it will give us the surface integral of the curl. Now one more thing which I want to tell you is that I have written it out here in the form of remark. What it is, that what I have written here is same. Same means this value would turn out to be same if this circular path C, here this is the C of the hemisphere and here this C of the cone, if they are the same circle, that means of the same radius. So if they are the same C, same closed path C, so now it does not depend, the surface integral of the curl does not depend on this surface. Either it is on the upper side it is a hemisphere or on the upper side it is a cone, so that doesn't matter, because from the above we see that curl of this would turn out to be line integral over that curve C. In both the cases the line integral is the same, and hence whether the upper curve is a hemisphere or a cone, so that doesn't matter, and we will get the, what I have written here as same. Same means we will get this quantity as the same. So that is why this remark I have told you here. Okay. So now we come to the questions. So our first question is that verify Stokes theorem for this F, where S is the upper half of the sphere and C is its boundary. Whenever there is a question on the verification, either it is Gauss divergence theorem or it is Stokes theorem or it is Green's theorem, always the question becomes a little bit lengthier, because I have to do two things. First of all, on the left hand side I have to calculate, say for example in this case, the line integral, and on the right hand side I have to calculate the surface integral. Then both things I have to see that they are coming out to be equal. Hence verification part is always a little bit lengthier one. So let us verify the Stokes theorem for this one. Now the sphere hemisphere part is open one, as I told you in the above by the diagram. So we can apply the Stokes theorem. That is the piecewise smooth as well, that I told you. So here C, what is my C? C is the circle in xy plane and its equation is given by this x square plus y square equal to 1 and z equal to 0. So I got the C. So first of all I calculate the LHS. LHS means line integral over this path. So what is it? This is this one. That is line integral of f dot dr. So let us see. So what is my f? This I part, j part, k part. So if I dot product it with respect to dr, what is dr? The dx I cap, dy j cap plus dz k cap, like that. So what I will get? X part, with x part I mean dx, y part dy, z part dz. Z part means from above, above means from here. X part means the I part. Okay. So here it turns out to be this. Now I make use of this equation, that is z equal to 0. So as z is equal to 0, so dz would also be equal to 0. So which part? This part would become 0, this part would become 0. So I would left out with the first one only. So let me scroll it a little bit up. So this part we are only left out. So let us convert it into one parameter. So circle, I take x equal to cos t, y equal to sin t, where t is ranging from 0 to 2 pi, and let us substitute it out. So this is the range of t 0 to 2 pi. In place of here 2x, so it is 2 cos t minus y means minus sin t. Now dx also I have to convert it in terms of t, so dx by dt into dt. So these are the things I have put out here. Now let us find out dx by dt and see what happens. So it is 2 cos t minus sin t, dx by dt is minus sin t. And if I multiply it here, so inside it would become 2 cos t sin t. And what it would be? It would become minus sin 2t, and we know its integration. Similarly, the second part would become plus sin square t, and we know how to integrate it out. So that is quite simple one. So that part I have left it out. So you can easily verify that the answer would turn out to be equal to pi. So our LHS part is done. Now come to the RHS part. What is the RHS part? See, first of all I need to find out curl, then n cap, and then third thing is find the surface integral. So three things I have to do: find the curl, find the n cap, and then find the surface integral. So first and foremost thing is we are finding the curl of f. Curl of f is I cap, j cap, k cap, del by del x, del by del y, del by del z, and this is our f here. What is f? This is first part, this is second part, this is third part. So all the three parts I would write down in the determinant. So this is first part, second part, third part. And if I obtain their partial derivatives, so suppose I take the I cap here and this one is left. So what it turn out to be I cap and minus 2yz, and then this with respect to this. So what I would come, so del, just a moment, one part is hidden here. So it is a small arrow I am putting. So it becomes plus, and z square means 2yz. So this and this gets cancelled out. Similarly, the j part you would obtain that this would turn out to be 0 minus 0, and last part k you will get it this one. So you can easily see that how it has been obtained. Okay. So what I will get? Curl, I will get this one. Curl of f is equal to k cap. Now I need to find out n cap. N cap of the surface. So what is the surface here? Surface here is this, x square plus y square plus z square equal to 1 is the surface here. So nabla f, or you can say del f. So del f, the definition is this one, divided by magnitude of del f. So I obtain the numerator, so I will get 2x I cap, 2y j cap, 2j k cap, and denominator means its magnitude. So I will get 4x square plus 4y square plus 4z square. So what would the denominator become is, I can take 4 common, x square plus y square plus z square, and I know that this x square plus y square plus z square is equal to 1 on the whole of the surface of the hemisphere. So this becomes 1. So that means 4 multiplied 1 becomes 4. So that means the denominator is square root of 4, and which is equal to 2. So denominator turns out to be 2. From the numerator, this 2 and this 2 gets cancelled out. So ultimately what I will get? I will get xi, this one, xi plus yj plus zk I will get. So I have obtained n cap, I have obtained curl. So I will put it out here. Here means this. So in place of curl of f, I have put out k cap, and n cap is this one. So, if I put obtain the dot product, so it will turn out to be z ds. So, first two things I have done, that is find out the curl, find out the n cap and put it out in the equation or the expression. Now, I obtain this surface integral. So, what I will do? I will put the projection on the xy plane. So, this r is the limits on the xy plane. So, I have put it taken the projection over the xy plane. So, this is the formula for that projection dx dy by modulus of n dot k cap. What is n? N here is this one. If I obtain k cap with this, so I will obtain z here and z is here. So, z and z gets cancelled out. So, I will get the dx dy. What are the limits? So, now let us see. When we project the hemisphere over the xy plane, so I will get the circle. What is my circle here is this, okay, and x is ranging from -1 to 1 and y is upper part is positive root, below part is negative root this one. So, these are the limits for that one, and I am leaving it out to you to calculate this double integral over this portion. There are two ways. One way is here you can take the dx, eliminate from here and dx here. Now, take the limit with respect to y and obtain it answer, or you can directly apply one concept, that is application of double integral in finding the surface area and volume. So, what was that? If I am taking a region R and if I take here as 1 dx dy. So, what does this represents? So, this represents what? Area of region R. So, this is the application of double integral. So, from there I am importing that thing here. So, here what is my region R? Region R is circle on the xy plane with the radius as 1. So, what is its area? Pi into r square. So, that means its area is pi. So, you can directly apply that application part here and obtain the value as pi here, that this double integral would turn out to be equal to pi, and hence what is our LHS equal to RHS, and hence Stokes theorem verified. Now, let us take one more question. Purposefully I have taken it in plane. Basically, there is no z cap here. You can see that f is this and here around the rectangle is in 2D plane. So, purposefully I have taken this to show you something else, which I will tell you at the end, that what I wanted to show you. So, first and foremost thing is given to me that verify Stokes theorem. So, what is the region is this rectangular region is there. So, it is basically what? This is a flat surface. So, surface it is open one. So, it is of this type, which I had told you in the diagram. See this type, I had given you an example. So, it was some wavy form, but here I am taking it as a flat surface, but that is basically not the closed one. So, what would be the C? C would be its boundary. So, there also the C would be the boundary of the rectangle. So, we come here. So, I have drawn the rectangle on the right hand side, this, that from -A to A, then above up to B and like that, which is quite easy one, you can see that one. Okay. So, now first of all I find the left hand side means the line integral. So, line integral basically I would calculate it one line along this line, along this line, along this line. You can say that it is a closed curve on this, so I can apply the Green's theorem as well, but purposefully I am not applying that one. I have to do it separately, okay, because my main job is basically to show that one. That is why I am not taking that. So along AB, along BC, along CD, along DA. So I calculate the line integral. Along first two I will show you, and rest two you can try at your own. So that is why I would leave that one part. So first and foremost thing is I obtain it along AB. AB means along this line. Okay. So we observe that throughout this y is 0, and hence dy is also 0, and range of x is minus a to a. So I obtain f dot dr. What is my f? F I take it from here, x square plus y square minus 2xy. So this is x square plus y square minus 2xy. With respect to dot dr means dx and dy along AB. Now I put the value of y as 0 and dy as 0, so I will obtain only x square. Now I put the values of limits of x, that is minus a to a, and ultimately this answer would turn out after integrating it. So this is along AB. Now I obtain along the vertical one, that is BC along this one, okay, along BC. So again along BC I am showing the diagram as well. So what is the value of x is throughout A, and hence dx is 0, and y is ranging from 0 to B. So I scroll it up now. So again this part is same, f dot dr would be the same throughout in all the cases. So but here wherever it is dx, that part is 0. So first part is gone. In second part, in place of x, I would put the value as a. So it would become minus 2ay and dy, and put the values of y from 0 to b. So this integral we would obtain. It is a quite easy one, so I would get this as the integral. So along first two lines I have obtained, that means along this, along this. So this part and this part I have written it directly because you can obtain in a similar way along CD and DA. So what I have written it out here, similarly along CD, so directly I have calculated out and written here. Along DA, it turns out to be this. So along the four lines I have obtained it. So summing those, that means adding those, doing the plus, we will obtain finally that f dot dr line integral turn out to be minus 4ab square. So left hand part is done. Now I obtain the right hand part. So there I need three things. First of all curl, then n cap, and then the surface integral. So first and foremost thing is in curl. So I, j, k, del by del x, del by del y, del by del z, and the three quantities of the f, x square plus y square first, minus 2xy, then 0. Evaluating it out, it will turn out to be minus 4y and k cap. So curl is now with us, and we are in the xy plane. So our right hand thumb rule, that means the n cap is turning up to be the k cap. So next we obtain this dot product, so will turn out to be minus 4y, and last one is the surface integral. So we put the value here in the surface integral. Okay. So what are the range? X, please see the range of x. Range of x is from here. Range of y is from 0 to b. So these are the range of x and y. Why I need the range of xy? Because I am, say, here, what I had seen. Suppose this is the figure. So I take the projection there. So here I am taking the projection on xy plane. Basically it is already on the xy plane. So projection means the same thing. So as we are already in the xy plane, so if I project this on the xy plane, so that means I will get the same thing. So that is why the limits are exactly the same. And I apply the formula of projection on the x by dx dy by modulus of n dot k cap. What is n? That is k cap. So k cap dot k cap would turn out to be equal to 1. So that means denominator is gone. So what I will get? Only the numerator, that is dx dy and minus 4y. So this is the limit of x, this is the limit of y. So one by one putting these, this is quite easy one. So you can calculate it out, and turns out to be minus 4ab square, and hence this thing is there and Stokes theorem verified. Basically what we have seen that in two-dimensional plane, basically Stokes theorem is nothing else but the Green's theorem. That is why I wanted to tell you this thing, and hence I have taken an example or question from the two-dimensional plane. So what was our Green's theorem was, that means if I am having, this is P, this is Q. So what was there? Double integral over R del Q by del X minus del P by del Y, and then dx dy. So what I will obtain? So left hand side was the C, line integral over the closed path would equal to this. So what is right hand side? Let me calculate. So double integral over R del Q over by del X, that means this. So it will give me minus 2y minus del P by del X, sorry, del P by del Y. So it will also give me 2y. So ultimately I will get over R minus 4y dx dy. So by Green's theorem I would have obtained minus 4y and then integration over that region. And by Stokes theorem also, right hand side you see, right hand side what I am getting? I am getting this minus 4y and over that region R. So we are getting the same thing. So that means in 2D plane, Stokes theorem is nothing else but the Green's theorem. So it is a generalization of that in the 3D we can say. So for that is why I told you that for purposefully I am taking this in the 2D plane. And one question as I am giving you as a homework, that by using Stokes theorem, this was the property while discussing the differential calculus of the vector. We had done this one, but by the other method. So here you have to try it out by using the Stokes theorem. So this is your homework, and with this this topic comes to an end, as well as our syllabus also comes to an end, and that's all about whole of the course of engineering mathematics part number 1. So I wish you all the best for your future endeavors and best of luck. Thank you very much for watching. Hello everyone.